The flaw is not the agent, it is the assumption that agents can manage their own integrations. Most organizations deploying copilots and custom bots in 2026 are building the same mistake they made with point-to-point APIs a decade ago. They are creating direct connections, scattering credentials across systems, maintaining no central state, and enforcing zero cross-tenant governance. What actually works is the opposite. Agents should reason, but they should not execute alone. If you are listening to this, you probably already have multiple copilots running inside your Microsoft 365 tenant. Maybe you have a Teams bot for IT support, a Copilot Studio agent for customer service, and a handful of Power Automate flows, handling notifications and approvals. Each one was built by a different team. Each one solved a local problem, and each one probably impressed the room when it was demoed. But here's the question nobody asks in those demos. They ask what happens when 10 of these bots need to coordinate the same end-to-end process. They do not ask what happens when an employee onboarding workflow starts in one system, waits for an approval in another, provisions resources in a third tenant, and then checks back after 30 days. That is not a conversation. That is a long-running business process that crosses boundaries, survives failures, and remembers what it was doing. And no chatbot can handle that alone. The research on enterprise AI in 2026 is clear. The sophistication of the underlying large language model matters less than the environment in which the agent acts. You can have the best reasoning engine in the world, but if it is wired directly to a dozen APIs with its own credentials, its own error handling, and its own business logic, then it is not an enterprise agent. It is a script with a nice interface. And scripts do not scale. The chatbot mirage, when demos become liabilities. Every organization starts in the same place. A department builds a bot. The bot answers questions from a SharePoint site or pulls records from Dataverse. It works in a 30-minute demo. People applaud. The project gets budget. And then another department builds another bot for a different use case, connecting to a different set of systems with a different set of credentials. This is exactly how Copilot Studio and Power Platform are designed to be consumed. Citizen developers and business analysts can spin up conversational agents without writing code. They can add knowledge sources, define tools, and set triggers so the agent runs autonomously when an email arrives or a ticket is created. The tutorial videos make it look effortless. And for a single use case inside a single tenant, it mostly is. The problem begins when you multiply this pattern. The IT support bot connects directly to Microsoft Graph to read group memberships. The sales notification flow calls Dynamics 365 with stored credentials. The customer service agent writes tickets to ServiceNow using a separate integration. None of these bots know about each other. None of them share state. And if the CRM API changes or the organization moves to a new incident management platform, every dependent bot must be updated individually. In many cases, the original developers have moved on. The integration code is buried inside prompts, tool definitions, and connection strings that nobody has fully inventoried. Governance teams discover they cannot answer basic questions about which agents can read HR data or send emails on behalf of users. Compliance auditors look for a central log of cross-tenant actions and find nothing because each bot logs to its own silo. This is the chatbot mirage. It is local intelligence without global coherence. It is impressive demos that mask systemic fragility. The bots are not bad. The architecture underneath them is point-to-point poison, the integration trap. Here is the number that should terrify every architect. The number of connections in a point-to-point integration model grows with the product of agents and systems. 3 agents talking to 5 systems is not 15 manageable connections. It is 15 separate implementations of authentication, retry logic, business rules, and error handling. Add a 4th agent and the problem does not grow linearly. It multiplies. Change becomes expensive and risky. When a critical business rule changes, every automation and agent that encodes that rule must be located, updated, tested, and redeployed. Some will be found quickly, others will be forgotten until they break in production. During transitions, some agents may use the old system while others use the new one, leading to inconsistent data, duplicate records, and customer-facing errors. Security and compliance controls are decentralized. Multiple app registrations, secrets, and keys proliferate, each with its own permission set and lifecycle. Security teams struggle to maintain least privilege access because each bot was configured by a different person with a different understanding of what the bot actually needs. Access reviews become a paper exercise. Revoking access for one agent might inadvertently affect others if they share a credential, or it might be overlooked entirely if the inventory is incomplete. Observability is fragmented. When something goes wrong, there is no central place to see the chain of actions across different agents and tenants. Troubleshooting requires spelunking through logs in many different services, correlating timestamps across disconnected systems, and hoping someone remembers how a specific bot was wired together 6 months ago. Point-to-point integrations also struggle with long-running processes. A bot that tries to handle an employee onboarding workflow on its own must implement its own persistence, correlation IDs, timers, and retry logic. It must remember where it was when a server restarts. It must handle the case where an approval takes 3 days instead of 3 minutes. Most bots do not implement this well. Some do not implement it at all. They assume the process is a single conversation, and that assumption is broken. The cross-tenant nightmare. Most of this chaos happens inside one tenant, but many real organizations operate more than one. Mergers and acquisitions leave you with multiple intra-directories. Regional sovereignty requirements force data into separate tenants. Subsidiaries and joint ventures need controlled collaboration. Partner organizations want to share processes without sharing credentials. Traditional integration approaches assume a single tenant architecture where all resources live under one identity authority. Cross-tenant scenarios break that assumption immediately. A service principal in one tenant cannot simply call an API in another. Tokens must be obtained for resources in different directories. Administrators must coordinate permission grants while maintaining security policies that may conflict. Microsoft Entra does provide cross-tenant collaboration features. B2B guest accounts let users from one tenant access resources in another. Multi-tenant applications can be registered in one tenant and granted permission in others, subject to an admin consent process. These mechanisms work for human users and carefully designed applications, but they were not built for dozens of autonomous agents making unattended API calls across boundaries at machine speed. An orchestration approach that does not explicitly address cross-tenant identity and authorization will run into friction at the first serious deployment. The bot works in the demo tenant. It fails in production because the managed identity cannot be assigned directly to another tenant. The developer switches to a client secret as a workaround. That secret gets rotated. The bot breaks at 2 in the morning, and nobody can figure out why because the error is buried inside a prompt response instead of a centralized workflow log. This is not a corner case. For organizations that have invested heavily in Microsoft 365 and Power Platform, multi-tenant reality is the default, and most agent architectures ignore it until it is too late. Why agents need memory? The stateful gap. There is a fundamental distinction that most bot builders miss. Stateless automations execute quickly in response to a single event, and they do not maintain long-term state beyond basic logging. A Power Automate flow that sends an email whenever a SharePoint item is created is stateless. Each run is independent. It starts, it acts, it finishes. If the server restarts mid-run, the flow might fail, but it does not need to resume from where it left off. Stateful orchestrations are different. They maintain a notion of process state over time. They handle multi-step interactions. They pause for hours or days. An employee onboarding workflow that starts when an offer is accepted, then waits for various approvals, triggers provisioning, sends welcome communications, and checks back after 30 days is inherently stateful. It must remember where it is. It must survive restarts. It must handle partial failures without starting over from the beginning. Copilot Studio handles reasoning. It interprets user intent, plans multi-step actions, and interacts conversationally. But it was not designed to be a workflow engine. It does not persist state across long-running processes. It does not manage correlations, timeouts, compensating actions, or cross-tenant handoffs. Logic Apps, by contrast, was built for exactly this kind of business process orchestration. It can pause and resume workflows, persist state to Azure storage, recover from failures, and interleave human and machine steps. The research on agentic workflow patterns in 2026 converges on a simple truth. Copilot Studio should handle the reasoning layer. Azure Logic Apps should handle the execution and integration layer. When you try to make Copilot Studio do both, you end up with a reasoning engine that is also responsible for persistence, retry, logic, and cross-system coordination. That is not a good division of labor. It is like asking your brain to also pump your blood. The nervous system exists for a reason. This is the stateful gap, and it is the single biggest reason why autonomous agents fail at enterprise scale. They can think, but they cannot remember. They can act, but they cannot coordinate. And without a stateful orchestration layer between the agent and the enterprise, every long-running process is a liability waiting to happen. The nervous system, how Logic Apps changes everything, so the model is broken. But the fix is not another platform, and it is not a bigger large language model. The fix is architecture. Specifically, it is treating your agents like muscles that connect to a central nervous system instead of brains that connect to everything directly. In a human body, muscles do not contain their own intelligence about when to contract or how to coordinate with other muscles. The nervous system handles perception, decision routing, and action coordination. The muscles execute, the nervous system governs, and if you sever the connection, the muscle may still have potential energy, but it cannot act in a coordinated way. Your organization is full of muscles right now. Copilots in Outlook, bots in Teams, flows in Power Automate, custom agents built on Azure OpenAI. Each one has local capability, but none of them are connected to a central nervous system that coordinates what they do, when they do it, and how they hand off to each other across tenant boundaries. Azure Logic Apps can function as that nervous system. It is a workflow engine built for declarative orchestration with deep connectors into Microsoft 365, Dynamics, Dataverse, Azure services, and hundreds of third-party APIs. It can host stateful orchestrations that span multiple systems and tenants. It can be triggered by events from agents, encode the authoritative business process, and call back out to agents or human users as needed. When identity is handled via managed identities and workload identity federation, this orchestration layer can operate securely at scale without spreading secrets and static credentials across every bot in your environment. The key shift is this. Agents should call the orchestrator, not the backend systems directly. The orchestrator exposes well-defined operations that represent business-level capabilities. Initiate cross-tenant onboarding for candidate X, open a Severity 1 incident, start a partner data sharing workflow. The agent does not need to know which Azure subscriptions or graph endpoints are used, which tenants must be contacted, or which approvals are required. It simply calls the orchestrator. The orchestrator maintains the canonical process definition, the state, the error handling, and the audit trail. This separation of concerns allows agents to focus on interpreting user intent and interacting conversationally, while the orchestrator focuses on reliable, policy-compliant execution across systems and tenants. It mirrors established software architecture patterns like facades, anti-corruption layers, and Saga orchestrators. And for organizations already invested in Microsoft 365 and Azure, Logic Apps is the most natural candidate to implement it. Standard versus consumption. Choose wisely. But not every Logic app deployment can pull this off. There is a choice you have to make first, and most people make it wrong. Azure Logic Apps offers two principal hosting models. The consumption model runs multi-tenant Logic apps in a shared environment and charges based on actions executed. It is easy to start with, especially for smaller workloads or sporadic automations. The portal experience is friendly, and you can build a working flow in minutes. For many citizen developers, consumption feels like the obvious path. The standard model hosts Logic apps in single-tenant infrastructure based on Azure functions. It supports improved performance, virtual network integration, custom connectors, and the ability to organize multiple workflows into a single app. It also integrates with Azure DevOps, GitHub, and infrastructure as code tools. Workflows are stored as JSON definitions that can be version controlled, diffed, reviewed, and deployed through pipelines. For autonomous agent orchestration, consumption is a liability. It supports only stateful workflows, which is good, but it has concurrency limits and less control over the underlying compute. Its environment and data loss prevention model can become complex at scale, and its lifecycle management and DevOps integration, while improved over time, are not as deep as Logic App Standard with code-first workflows. Standard is the only serious option for a nervous system. It gives you the compute isolation, networking controls, and deployment rigor that enterprise orchestration demands. It lets you run stateful and stateless workflows side by side in the same Logic app resource, which matters when you need fast synchronous responses for some operations and durable long-running processes for others. And it positions you for the agent loop action and other AI-integrated capabilities that Microsoft is delivering primarily through the standard runtime. The research on Logic Apps, standard versus consumption for orchestration workloads in 2026 is consistent. If you are building a mission-critical integration backbone that will coordinate agent behavior across business units and tenants, you need the control that standard provides. Consumption is fine for personal productivity flows and departmental automations. It is not fine for the central nervous system of your enterprise AI architecture. Stateful workflows, the agent's memory. Once you are on standard, the first capability you need to understand is state, and this is where Logic Apps separates itself from every other automation tool in the Microsoft stack. Stateful workflows persist their state to external storage at multiple checkpoints throughout a run. Every action, every decision, every wait state is recorded. If the runtime restarts, the workflow resumes from its last checkpoint instead of starting over. If an action fails, you can inspect exactly what the inputs and outputs were at that specific step. If an approval takes 3 days, the workflow sleeps efficiently, consuming minimal resources while it waits, and wakes up precisely when the response arrives. This persistence is not just a reliability feature, it is a memory feature, and memory is what turns a reactive bot into a proactive agent. An agent that initiates a cross-tenant onboarding process needs to remember that it is waiting for a background check in one tenant and a manager approval in another. It needs to know that Step 3 cannot begin until Step 2 completes. And it needs to handle the case where Step 2 fails with a specific error code that means the target system is down for maintenance. In 2024, Microsoft introduced the agent loop action in Logic Apps Standard. This is a first-class workflow action that hosts the agent's reasoning loop driven by a large language model. It exposes tools via Logic Apps connectors and custom APIs, and it maintains memory and state across iterations within the workflow run. The agent thinks about its goal, acts by invoking a tool, learns from the result, and then thinks again. This think, act, learn cycle is embedded directly in the workflow engine, not bolted on top of it. The difference between a bot that forgets and an agent that persists intent is the difference between a conversation that starts fresh every time and a process that survives interruptions, learns from partial results, and continues toward a goal across hours or days. Stateful workflows give agents that persistence, And without it, you do not have autonomous agents. You have stateless scripts that pretend to be intelligent. Connectors as neural pathways. Memory means nothing if the agent cannot reach the muscles. In the nervous system metaphor, the connectors are the neural pathways that carry signals from the orchestrator to the systems that do the actual work. Logic Apps ships with hundreds of built-in connectors for the Microsoft ecosystem. SharePoint, OneDrive, Outlook, Teams, Dynamics 365, Power BI, Dataverse, Azure Service Bus, Event Grid, Key Vault, Storage. These connectors encapsulate authentication, endpoint details, and API semantics into actions that appear in the workflow designer. When a Logic app uses a connector, it configures a connection that can be based on a managed identity or a secure secret stored in Key Vault rather than on user credentials or hard-coded strings. For systems without ready-made connectors, Logic apps can call HTTP-based APIs using the built-in HTTP action. But the more robust pattern for enterprise orchestration is the custom connector. Custom connectors allow developers to describe an API using OpenAPI or other metadata, and Logic Apps then exposes it in the designer like any other first-class component. This is particularly useful for internal APIs, legacy systems, and proprietary enterprise logic that needs to be surfaced to agents in a controlled, governed way. In a nervous system architecture, connectors and custom connectors become the nerves through which the orchestrator reaches muscles and sensors. Agents do not need to know how to call these connectors directly. They simply request that the orchestrator perform certain actions. The orchestrator manages the connection, the authentication, the retry logic, and the error handling. This division of labor makes it easier to update integrations as APIs change, and it allows security teams to centralize and scrutinize every connection that crosses a tenant boundary. By 2026, the dominant pattern for custom connectors is what architects call logic in API. Proprietary enterprise logic such as pricing engines, eligibility rules, and risk scoring is wrapped as secure, lifecycle managed APIs with clear contracts. These APIs are then described with open API specifications and published as custom connectors inside Logic Apps. The result is a standardized interface that any agent or workflow can call without understanding the underlying complexity. And when the business rule changes, you update the API and the connector. You do not update a dozen different bots. Orchestrator-first architecture, which brings us to the pattern that makes all of this work. And it is the exact opposite of how most teams build agents today. The naive pattern is to give the large language model a set of tools that directly call external systems. The agent sees functions for reading SharePoint, sending emails via Graph, updating Dataverse, and calling a custom API. It decides which to invoke, constructs the parameters, and executes the call. This works in small demos. It fails in production because the agent has direct access to low-level systems, with no central place to enforce business rules, manage state, or log actions for compliance. The robust pattern is orchestrator-first tool calling. The agent sees a different set of tools. These tools do not call external systems directly, they call Logic Apps. Each tool maps to an HTTP-triggered workflow that represents a business-level capability. Initiate cross-tenant onboarding, request incident escalation, start partner data sharing. When the agent calls such a tool, the Logic app receives the request and implements the full orchestration. It validates the request against policies. It calls Microsoft Graph or other APIs via managed identity. It waits for approvals, it handles errors, and it returns a structured response that the agent can use to inform its next reasoning step. This separation has several advantages. It constrains what the agent can do to actions that are explicitly designed and reviewed by humans. It centralizes process logic in Logic Apps, where it can be versioned, tested, and governed through standard DevOps pipelines. It allows identity and permissions to be managed via managed identities and Entra ID rather than via custom tokens buried inside the agent's prompt or configuration. It simplifies debugging and observability, since each tool call corresponds to a well-defined Logic app run with full run history. For the M365 FM audience, this pattern is the bridge between Copilot Studio and Azure. It lets you keep the conversational experiences and reasoning capabilities that Copilot Studio does well, while moving execution, state management, and cross-tenant coordination into Logic apps where they belong. Agents reason, orchestrators execute. That is the architecture that scales. The identity problem, where production implementations die. Now, everything we have covered so far is architecture, and architecture is easy to draw on a whiteboard. What actually breaks in production is not the workflow, it is the identity layer. And this is where most implementations die before they ever reach a second tenant. In Microsoft Entra ID, workloads authenticate using service principals. An application is registered, permissions are granted, and a service principal object represents that app's identity within a tenant. Traditional patterns rely on client secrets or certificates that the application uses to obtain tokens. Secrets must be stored, rotated, and protected. Certificates have life cycles that must be managed. And as the number of apps grows, the secret sprawl becomes a serious operational risk that security teams dread. To address this, Azure introduced managed identities. A managed identity is essentially an automatically managed service principal attached to an Azure resource such as a Logic app, function app, or app service. The platform handles the lifecycle of the credentials, allowing the resource to obtain tokens for Azure services and Microsoft Graph without storing secrets in code or configuration. Managed identities can be system-assigned, tied to the lifecycle of the resource, or user-assigned, which is a standalone identity that can be shared among multiple resources. This works beautifully inside one tenant. The Logic app has a managed identity. You grant that identity permission to read from SharePoint or write to Dataverse. The platform handles the token acquisition behind the scenes. There are no connection strings to leak. There are no secrets to rotate. And if the Logic app is deleted, the system-assigned identity is automatically cleaned up. But cross-tenant is where this pattern hits a wall. You cannot assign a managed identity from tenant A directly to a resource in tenant B. The identity authorities are separate. The token endpoints are different. And the consent frameworks that work for human users do not translate cleanly to unattended workload authentication at scale. This is the exact moment where most teams give up and reach for a client secret. They create a service principal in the target tenant, generate a secret, and embed it somewhere in the agent's configuration or the workflow's connection string. It works. It is also exactly the pattern that creates the security sprawl we are trying to escape. The secret expires, the bot breaks, someone generates a new secret and updates it in a configuration file that nobody remembers to audit. And 6 months later, your compliance team finds an active credential that should have been revoked. The cross-tenant identity problem is not a footnote. It is the primary reason why multi-tenant agent orchestration fails in production, and solving it requires a different approach to authentication entirely. Secretless authentication, managed identities, and workload federation. The fix is not going back to secrets. It is going deeper into identity federation. And by 2026, Microsoft has built the tooling to make this practical. Managed identities remain the foundation. For resources inside a single tenant, they are the correct and only pattern you should use. But for cross-tenant scenarios, you need workload identity federation. This is a pattern in which a workload running in one environment can authenticate to Entra ID in another tenant without secrets by presenting a trusted token issued by its own identity provider. Here is how it works in practice for Logic Apps. You configure a trust relationship in the target tenant using the Azure AD token exchange mechanism. The source workload, which could be a Logic app with a managed identity in tenant A, presents a token from its own identity platform. The target tenant validates that token based on the pre-configured federation setup and issues an access token that the workload can use to call APIs in the target tenant. No client secret is ever created, stored, or rotated. The trust is based on cryptographic verification, not shared passwords. Microsoft Entra Agent ID extends this foundation with identity and security layers designed specifically for AI agents. It provides blueprints that describe an agent's permissions, behaviors, and identity model. It lets you define whether an agent should use a workload identity pattern or a user-delegated pattern, and it governs how many agent identities exist per blueprint, allowing you to choose between one shared identity for a class of agents or many granular identities for individual agent instances. This matters enormously for orchestration. When an autonomous agent calls a Logic app to initiate a cross-tenant process, the call itself can be authenticated through Agent ID. The orchestrator then uses its own managed identity or federated trust to execute actions in the target tenant. Every step of the chain is authenticated, authorized, and logged. There are no shared secrets buried in configuration files. There are no long-lived credentials that can be stolen or forgotten. The zero-trust posture this enables is straightforward. Verify explicitly. Every request is authenticated and authorized based on identity, device, location, risk, and policy. Use least privilege access. Granular permissions and just enough access are enforced at every step. Assume breach. Segment, monitor, and log everything, including cross-tenant flows. Logic apps with managed identities and workload identity federation give you the technical primitives to implement these principles without inventing custom security code. This is secretless authentication at enterprise scale, and it is the only authentication model that makes autonomous agent orchestration viable across multiple tenants. Custom connectors, the contract layer, but identity only gets you through the door. What happens inside the room matters just as much, and inside the room, agents need boundaries. They need contracts that tell them exactly what they can do and exactly how to do it. Without those contracts, agents hallucinate capabilities. This is where custom connectors become critical. A custom connector is a packaged description of an API, most often using OpenAPI or Swagger, plus authentication configuration, operation definitions, and schema mapping. It is surfaced as a first-class component in the Logic Apps Designer, which means it appears alongside built-in connectors like SharePoint and Outlook. The workflow author selects it, configures the connection, and uses typed fields just like any other action. For proprietary enterprise logic, custom connectors are the contract layer that keeps agents from improvising. When an agent needs to calculate a price, check an eligibility rule, or score a risk profile, it should not be writing raw HTTP calls with handcrafted JSON payloads. It should be calling a custom connector that exposes a typed action named calculate price or check eligibility with defined inputs and outputs. The agent knows exactly what parameters to provide, the orchestrator knows exactly what response to expect, and the security team knows exactly what business capability is being invoked. By 2026, the dominant pattern for exposing internal capabilities is logic in API. Domain-critical logic lives in internal services. Those services are wrapped with open API specifications. The specifications are published as custom connectors inside Logic Apps, and the connectors are versioned, governed, and deployed through the same CI/CD pipelines that manage the rest of the infrastructure. This has a profound effect on agent behavior. When an agent's tools are well-defined custom connectors, it cannot hallucinate a capability that does not exist. It cannot call an endpoint that has not been reviewed and published. And it cannot bypass business rules by constructing its own raw API calls. The connector is the contract is the guardrail, and the guardrail is what makes autonomous agents safe at scale. Governance teams benefit too. Instead of reviewing every prompt and every tool definition inside a dozen different bots, they review the open API contract once. They approve the operations, the scopes, and the data types. And every agent that uses that connector inherits those boundaries automatically. When the business rule changes, the API is updated, the connector is versioned, and every workflow that uses it gets the new behavior through standard deployment processes. Error handling as intelligence. And once the agent is inside and doing work, it will fail. This is not a possibility. It is a certainty. APIs go down, tokens expire mid-flight, rate limits kick in during peak hours, and data validation fails because a downstream system changed its schema without telling anyone. The question is not whether failures happen. The question is whether your architecture can handle them without human intervention every single time. Logic Apps Standard provides the error handling primitives that make this possible. Scoped actions let you wrap a set of steps in a container that can succeed or fail as a unit. Configure run after settings let you define alternative paths for success, failure, skipped actions, and timeouts. Do until loops with delays implement retrees and backoff. And the terminate action lets you end a workflow gracefully when an unrecoverable error is detected. But agentic workflows in 2026 go beyond these classic patterns. They use what architects call guarded try-catch, where the AI agent itself participates in error triage. When a failure occurs, the orchestrator captures the error details and presents them to the agent's reasoning loop. The agent analyzes the error type. It decides whether this is a transient issue that warrants a retry, a permission failure that requires escalation to a human, or a data problem that needs a compensating action. It then instructs the orchestrator on the next step. This is self-healing workflow behavior. The agent loop action in Logic Apps Standard maintains memory across these iterations. It remembers that step 3 failed with a rate limit error. It remembers that the system recommended waiting 60 seconds before retrying, and it remembers that the retry succeeded, so the process can continue to step 4 without starting over from the beginning. Adaptive retry takes this further. Instead of static retry counts with fixed delays, the orchestrator uses the error context to choose the right recovery strategy. A rate limit from Microsoft Graph probably means you should back off and retry with exponential delay. A permission-denied error from a cross-tenant call probably means the federation trust has expired and a human needs to reauthorize it. A schema validation error probably means the downstream system changed its contract and the integration team needs to update the custom connector. These are fundamentally different failures. They deserve fundamentally different responses. The difference between a fragile bot and a resilient agent is not the absence of errors. It is the architecture that surrounds the error when it happens. Stateful workflows with scoped error handling, adaptive retry, and AI-assisted triage turn failures from show-stopping events into managed deviations. The process survives, the state persists, and the agent learns what to do differently next time. Governance, from human in the loop to human on the loop. Which brings us to the governance question that nobody wants to ask. If agents can reason, execute across tenants, handle errors, and retry on their own, then the question is what exactly humans are for. And the answer depends entirely on what the agent is doing. Human in the loop means the agent stops and waits for explicit human approval before taking any action that crosses a risk threshold. Every email send, every data modification, every cross-tenant provisioning action requires a human to click approve. This is safe. It is also slow. And at scale, it creates a bottleneck that defeats the purpose of automation. Human on the loop means the agent executes within predefined guardrails, and humans review exceptions, patterns, and outcomes rather than individual actions. The guardrails are enforced by the orchestrator, not by the agent's good intentions. The orchestrator checks policy before executing. It logs every action with full context. It raises alerts when anomaly detection flags unusual behavior. And it escalates to humans only when the deviation falls outside the predefined boundaries. For routine operations like updating a customer record, sending a standard notification, or querying a non-sensitive dataset, human on the loop is the correct model. The orchestrator enforces the guardrails, the agent operates within them, and humans review dashboards and reports to ensure the system is behaving as expected. For high-stakes transactions like financial transfers, personnel actions, or cross-tenant data sharing that involves regulated information, human in the loop may still be required. The orchestrator can route these actions through approval workflows automatically. It can present the human reviewer with the full context of what the agent is trying to do, why it is trying to do it, and what the consequences are. The human makes the decision, the orchestrator records the decision, and the agent continues or aborts based on that recorded outcome. Azure Logic Apps provides the run history and audit trails that make both models viable. Every action is logged with inputs, outputs, timestamps, and identity information. Tenant isolation policies can block or restrict shared connections across tenants, allowing only specific trusted tenants to be called. And intra-workload identities with conditional access policies can detect anomalous sign-in behavior and block risky agent actions before they execute. Governance is not a separate layer that you add after the agents are built. It is a property of the orchestration architecture. And if your orchestrator cannot enforce guardrails, log actions, and escalate exceptions, then you do not have governance. You have hope. A day in the life, how the nervous system actually runs. Let me walk you through a concrete scenario so you can see how this architecture behaves when everything is connected. Imagine a multinational company with 3 Entra tenants. Tenant A is the corporate headquarters in Amsterdam. Tenant B is a regional subsidiary in Singapore that operates under local data residency requirements. Tenant C is a partner organization that provides specialized logistics services. An employee in Amsterdam initiates a request through a Copilot Studio agent embedded in Teams. The employee says they need to onboard a new contractor who will work across all 3 entities. The Copilot agent interprets the intent, extracts the contractor's details, and calls a logic app in Tenant A via an HTTP trigger. The call is authenticated using the agent's Entra agent ID. The logic app in Tenant A receives the request and starts a stateful workflow. Step 1 is validation. It checks the contractor's details against corporate policy using a custom connector that talks to the internal HR policy engine. The connector returns a structured response. The contractor is cleared for basic onboarding, but flagged for additional security review because the role involves cross-tenant data access. Step 2 is routing. The logic app branches based on the policy response. Because the contractor needs access to Tenant B and Tenant C, the orchestrator initiates parallel sub-workflows. The sub-workflow for Tenant B uses workload identity federation to authenticate to the Singapore tenant's Entra instance. It calls a separate logic app that lives in Tenant B, passing the contractor details and the security flag. The Tenant B logic app handles local provisioning according to Singapore's data residency rules. It provisions a local mailbox, assigns regional security groups, and schedules a local compliance training session. Meanwhile, the sub-workflow for Tenant C uses a different federation trust to reach the partner tenant. It calls a custom connector that exposes the partner's logistics onboarding API. The partner system confirms the contractor's eligibility and returns a temporary access token with a 30-day expiration. The orchestrator stores this token in Azure Key Vault and logs the grant in the central audit trail. Step 3 is waiting. The main workflow in Tenant A pauses. It has initiated actions in 2 other tenants. It has recorded the pending security review flag, and it now enters a wait state that can last up to 30 days. During this wait, the workflow consumes minimal resources. Its state is persisted to Azure storage. If the runtime restarts, the workflow resumes exactly where it left off. 10 days later, the security team in Amsterdam completes the enhanced review. They approve the contractor through a Power App that writes an approval record to Dataverse. The Logic app was configured with a Dataverse trigger that watches for this specific approval status. When the record updates, the trigger fires and the workflow resumes from its wait state. Step 4 is completion. The workflow verifies that both Tenant B and Tenant C sub-workflows completed successfully. It checks that the security approval is on file. It sends a welcome email to the contractor using a shared mailbox connector. It provisions the final corporate resources in Tenant A, and it schedules a 30-day access review checkpoint by writing a follow-up task to a shared planner board. Throughout this entire process, no human manually coordinated the handoffs between tenants. No client secrets were exchanged across boundaries. No agent had direct access to every system. The Copilot agent reasoned about the request. The Logic Apps orchestrator executed the process. The state was maintained across 10 days and 3 tenants, and every action was logged with the identity of the caller, the time, the inputs, and the outputs. This is not science fiction. This is what the architecture delivers when you stop building siloed agents and start building a nervous system. how managed identity federation actually works. I want to go deeper on workload identity federation because this is the piece that most architects get wrong on their first attempt. And when they get it wrong, they revert to secrets. And secrets are the beginning of the end. Here is the actual pattern that works in 2026. In the source tenant, you have a logic app with a system-assigned managed identity. That identity is registered as an application in Entra ID. In the target tenant, you create a federated identity credential on that application registration. The federated credential trusts tokens issued by a specific source, which in this case is the managed identity token endpoint from the source tenant's Azure infrastructure. When the logic app needs to call an API in the target tenant, it first requests a token for its own managed identity from the Azure Instance Metadata Service. That token is a standard JSON web token signed by the Azure platform. The logic app then presents this token to the target tenant's token endpoint, along with the application ID of the registered app and the requested resource scope. The target tenant verifies the token signature against the Azure platform's public keys. It checks that the issuer matches the federated credential configured on the app registration, and if everything validates, it issues an access token for the target resource. The access token that the target tenant issues is scoped to the permissions that were granted during admin consent. If the app registration only has permission to read user profiles, that is all the access token can do. If it needs write access to SharePoint sites, that permission must be explicitly granted and consented. This is least privilege by design. Now here is the critical part that many teams miss. The federated credential is not a secret. It is a trust relationship. You configure it once through the Azure portal, ARM templates, or Microsoft Graph API. It contains the issuer URL, the subject identifier, and the audience. There is no password to rotate. There is no certificate to renew. And if the source managed identity is deleted, the federated credential becomes inert because the token requests stop. For multi-tenant orchestration, you repeat this pattern for each target tenant that your orchestrator needs to reach. The logic app in tenant A might have 3 separate federated credentials configured, one for tenant B, one for tenant C, and one for a development environment. Each trust relationship is independent. Each can be revoked without affecting the others. And each is monitored through Entra workload identities analytics, which can detect anomalous sign-in patterns and risky behavior. This pattern requires more setup than copying a client secret into a connection string. That is the point. The extra setup is the governance. Every trust relationship is explicit, documented, and auditable. And that is exactly what enterprise security teams need when they are asked to approve autonomous agents that operate across organizational boundaries. The agent loop action, what it is and why it matters. In 2024, Microsoft announced the agent loop action at Build, and by 2026, it has become the core primitive for agentic decision modeling inside Logic Apps standard. This is not a marketing feature. It is a fundamental change in what a workflow engine can do. The agent loop action is a first-class workflow step that hosts an AI agent's reasoning loop directly inside the Logic Apps runtime. It connects to an Azure OpenAI deployment or another supported model. It exposes a set of tools that the model can call. And it manages the iterative cycle of reasoning, tool invocation, and result evaluation within a single workflow run. Here is what happens when an agent loop action executes. The workflow starts the action with an initial prompt or goal. The action sends that goal to the language model. The model analyzes the goal, considers the available tools, and decides what to do next. It might decide to query a database, call an API, or ask a human for clarification. It returns a structured tool call request. The agent loop action receives the tool call request and routes it to the appropriate Logic Apps connector or custom action. It executes the tool, it captures the result, and it passes that result back to the language model as an observation. The model now has new information. It reasons again, it decides on the next step, and the cycle continues until the goal is achieved, an error occurs, or a maximum iteration limit is reached. What makes this powerful is that the loop maintains memory across iterations. The model sees the full conversation history of the loop, including every previous thought, every tool call, and every result. This means the agent can handle multi-step reasoning without losing context. It can recover from partial tool failures by trying alternative approaches. And it can explain its reasoning by referencing the sequence of actions it took. For the orchestrator-first architecture we have been discussing, the agent loop action sits at the agent boundary. The Copilot Studio bot or external front-end interprets the user's natural language request and translates it into a structured goal. It calls a logic app via HTTP trigger. The logic app executes the business process orchestration, which may include one or more agent loop actions for decisions that require reasoning. The agent loop handles the cognitive work. The surrounding workflow handles the execution, state, error handling, and cross-tenant coordination. This separation is clean, it is maintainable, and it is exactly what you need when your agent's reasoning capabilities will change every 6 months as new models are released. But your business process logic must remain stable and auditable for years. Building your first custom connector. Let me get practical. You have an internal API that calculates pricing for enterprise contracts. Right now, your Copilot agent is calling that API through a raw HTTP action with a handcrafted JSON payload. That works until the API changes its input format or until a citizen developer copies the HTTP call into another bot with slightly different parameters, or until the security team asks for an inventory of every place that calls the pricing engine and you realize you do not have one. The fix is a custom connector, and the process is simpler than most people assume. Step 1 is to document the API using OpenAPI. If your pricing API already has an OpenAPI specification, you are halfway done. If it does not, you create one. The specification describes the endpoint, the HTTP method, the authentication scheme, the input parameters with their data types, and the response schema. For a pricing engine, the inputs might include customer tier, product code, contract duration, and discount eligibility flag. The response might include base price, applied discounts, final price, currency code, and expiration timestamp. Step 2 is to create the custom connector in the Azure Portal or Power Platform Admin Center. You import the OpenAPI specification. You configure the authentication, which for an internal API might be Microsoft Entra ID OAuth or an API key stored in Azure Key Vault. The platform generates the connector definition and makes it available in the Logic Apps Designer. Step 3 is to test. You create a test workflow that uses the custom connector to call the pricing API with sample data. You verify that the inputs appear as typed fields in the designer. You verify that the response fields are available for downstream actions. And you verify that authentication works correctly with the chosen identity model. Step 4 is governance. You publish the connector to a specific environment or solution. You document what operations it exposes, what data it accesses, and what permissions it requires. You add it to your connector catalog so other teams can discover it. And you set up CI/CD so that when the pricing API changes, the OpenAPI spec is updated, the connector is regenerated, and the new version is deployed through a managed pipeline. Now, when an agent needs a price, it does not make a raw HTTP call. It calls the enterprise pricing connector. The orchestrator knows exactly what capability is being invoked. The security team knows exactly which workflows have access to pricing data. And when the pricing engine adds a new parameter for carbon offset calculations, you update the connector once. Every workflow that uses it inherits the new field automatically. This is what logic in API means in practice. Your proprietary business logic is wrapped in a contract. The contract is published as a connector, and the connector is the only thing agents are allowed to touch. Error routing patterns in detail. I want to spend more time on error handling because this is where beautiful architectures go to die in production. And I want to show you the specific patterns that prevent that death. The first pattern is the scoped try-catch. In Logic Apps Standard, you wrap a set of related actions inside a scope block. You configure the scope with run-after settings that define what happens when the scope succeeds, fails, is skipped, or times out. Inside the scope, you place the normal workflow path. Outside the scope, you place the error handling path. When an action inside the scope fails, the scope itself is marked as failed. The run-after trigger on the error path fires. The error path receives the failure details, including the action name, the error code, the error message, and the status. It can then branch based on the error type. A 429 status code from Microsoft Graph means rate limiting. The error path waits 60 seconds and retrieves. A 401 status code means the federated credential has expired. The error path creates an escalation ticket in ServiceNow and terminates the workflow gracefully. A 500 status code from an internal API means the downstream system is down. The error path logs the incident, sends an alert to the operations team, and enters a long wait state before retrying. The second pattern is the agent-assisted error triage. When a scope fails inside an agent loop action, the orchestrator does not just retry blindly. It presents the error context to the language model. The model reads the error code, the message, and the history of previous attempts. It classifies the failure. It proposes a recovery strategy. And the orchestrator executes that strategy. This is where the research on agentic error routing in 2026 gets interesting. The best implementations do not treat all failures the same. They categorize them into transient failures that warrant retry, permission failures that require human escalation, data failures that need compensating actions, and systemic failures that should abort the entire workflow. The classification is not hard-coded in the workflow JSON. It is inferred by the agent based on the error context and the process history. The third pattern is the compensating action. In long-running stateful workflows, some steps cannot simply be retried. If a workflow already debited an account and then failed on the next step, retrying the debit would double charge the account. The compensating action reverses the debit before the workflow attempts the sequence again. Logic Apps stateful workflows support this through carefully designed scope structures where each irreversible action is paired with a compensating action that runs only if the overall scope fails. These three patterns together, scoped error handling, agent-assisted triage, and compensating actions, are what separate a proof of concept from a production orchestration. They are not glamorous, they do not demo well, but they are the reason your agents keep running at 2 in the morning when the API you depend on goes down. Stateful versus stateless, when to use each. By now you are probably wondering whether every workflow in your nervous system needs to be stateful. The answer is no. And understanding when to use each type is critical for both performance and cost. Stateless workflows run entirely in memory. They do not persist intermediate state or run history to Azure storage. This makes them much faster and more scalable for short-lived operations. A stateless workflow can handle HTTP requests with low latency and high throughput because it is not waiting for storage writes between actions. But the trade-off is strict. The maximum execution time for a stateless workflow in Logic Apps standard is 5 minutes. If the workflow has not completed by then, it is terminated. There is no resume, there is no checkpoint, and there is no detailed run history for debugging. Stateful workflows persist state to external storage at every action. This adds input-output overhead and reduces raw throughput. But they can run for hours or days. They support callbacks, approvals, and external events. They resume after restarts, and they provide full run history with every input and output captured for debugging and audit purposes. For the nervous system architecture, you use both. Stateless workflows are your reflexes. They handle quick validation checks, simple lookups, and synchronous responses that an agent needs immediately. Stateful workflows are your long-term memory. They handle onboarding processes, multi-day approvals, cross-tenant coordination, and any process that needs to survive interruptions. Community benchmarks from 2025 and 2026 show a clear pattern. Converting a simple HTTP-triggered workflow from stateful to stateless under similar load conditions typically increases throughput by a factor of 3 to 5 and reduces latency by roughly half. These are not minor differences, they are architectural differences, and they matter when your orchestrator is handling hundreds or thousands of agent requests per hour. But the benchmark numbers come with a caveat. The performance gain only matters if the workflow fits the stateless constraints. If your process needs to wait for an approval or retry over hours or coordinate across multiple systems with unpredictable timing, then stateless is not an option. It is a trap, and the 5-minute limit will break your process in production when the CFO takes 3 hours to respond to an approval request. The correct pattern is to design your orchestration so that stateless workflows handle the fast, predictable paths and stateful workflows handle the slow, complex, multi-tenant processes. Both run side by side in the same Logic Apps standard resource. And the orchestrator routes agent requests to the appropriate workflow type based on the nature of the task. Real numbers, what this costs and how it performs. Let me be direct about performance and cost because executives will ask, and you need to have answers that are grounded in real measurements rather than marketing slides. Logic Apps standard runs on an app service plan or a functions premium plan. You pay for the underlying compute, not per action. This means that once you have provisioned the plan, your cost is relatively predictable regardless of how many workflows run. For a nervous system handling moderate enterprise load, a single app service plan instance might cost a few $100s per month. At higher scales, you scale out to multiple instances and the cost increases linearly with compute. Consumption-based Logic Apps, by contrast, charge per action execution. For low-volume scenarios, this can be cheaper. But for high-volume orchestration where workflows execute thousands of actions per hour, the per-action billing can quickly exceed the cost of a dedicated standard plan. The research on Logic Apps standard versus consumption for enterprise orchestration consistently shows that standard becomes more cost-effective once you cross a threshold of a few thousand action executions per day. Performance is harder to generalize because it depends on what your workflows do. A stateless workflow that calls a fast internal API and returns a result might complete in under a second. A stateful workflow that waits for 3 external approvals across 2 tenants might take 3 days to reach completion, but the actual compute time consumed is only a few minutes because the workflow sleeps efficiently between wait states. What matters for agent orchestration is throughput, latency for synchronous operations, and reliability for long-running processes. Stateful workflows in standard can handle high-throughput scenarios when designed correctly, but they will always have higher latency per action than stateless due to the storage persistence. The key is to use stateless for the fast path and stateful for the durable path, rather than trying to force every process into a single workflow type. For reliability, the numbers strongly favor standard. Stateful workflows with checkpoint persistence can resume after infrastructure failures, region outages, and runtime updates. The run history provides the observability that operations teams need to diagnose issues. And the integration with Azure Monitor, Application Insights, and Log Analytics gives you centralized logging across all your orchestration workflows. Tenant isolation and cross-tenant security configuration. I want to return to security for a moment because there is a specific configuration that many organizations overlook until it is too late. Azure Logic Apps supports tenant isolation policies that control whether connections can be shared across tenant boundaries. Historically, Logic Apps connectors allowed connection sharing via consent links. A user in tenant A could create a connection to an Office 365 resource and share that connection to workflows in another tenant. This created a significant security concern, A shared connection could silently grant broad access to resources in one tenant from another tenant if the sharing was not tightly controlled. To address this, Microsoft added tenant isolation policies. As a tenant administrator, you can now block access to and from your tenant through shared connections altogether. Or you can allow connections only to specific trusted tenants, explicitly listing which tenants are permitted. This is a critical control for any organization that operates in a multi-tenant environment or collaborates with partners. The recommended configuration for a nervous system architecture is to block shared connections by default and allow only specific tenants that have been reviewed and approved by your security team. Each allowed tenant should have a documented business justification, a reviewed federation trust configuration, and a monitored connection pattern. Anything else is blocked at the tenant boundary. This policy works in conjunction with managed identities and workload federation. Even if a tenant is on the allowed list, the actual authentication is handled through federated trust, not through shared connection links. The tenant isolation policy prevents accidental sharing. The federation trust ensures that only explicitly authorized workloads can cross the boundary, and the monitoring layer detects anomalies in cross-tenant traffic patterns. Together, these three layers create a defense-in-depth model for cross-tenant agent orchestration. The policy says who is allowed to connect, the federation says who is allowed to authenticate, and the monitoring says what is actually happening. Missing any one of these layers creates a gap that a determined attacker or a careless developer can exploit. Monitoring and observability for the nervous system. An orchestration architecture without observability is a black box that your operations team will learn to hate. And agent orchestration adds specific observability challenges because the process spans multiple systems, multiple tenants, and multiple reasoning iterations. The foundation is Logic Apps run history. Every workflow execution in standard is recorded with a unique run identifier, start time, end time, status, and a detailed action-by-action log. For stateful workflows, you can inspect the inputs and outputs of every action. For workflows that include agent loop actions, you can see the reasoning iterations, the tool calls, and the responses. But run history alone is not enough for a nervous system. You need distributed tracing. When a Copilot agent calls a logic app, which calls another logic app in a different tenant, which calls a custom connector that invokes an internal API, you need a single trace identifier that follows the request across all those boundaries. Azure Application Insights and OpenTelemetry integration in Logic Apps standard provide this capability. You configure a correlation ID at the entry point, and it propagates through every downstream call. You also need alerting, not generic alerts that fire every time a workflow fails, because workflows will fail. You need alerts that detect patterns. A sudden spike in rate limit errors from Microsoft Graph might indicate that your agent is making too many calls and needs throttling logic. A series of permission-denied errors across multiple tenants might indicate that a federated credential is expiring. A workflow that normally completes in 10 minutes but suddenly starts taking an hour might indicate a storage performance issue or a downstream API slowdown. Dashboards are the third layer. Your operations team needs a single pane of glass that shows the health of the orchestration layer. The metrics that matter include how many workflows are running right now, how many are in wait states, what the average completion time is for cross-tenant onboarding processes, and how many agent loop actions required more than 3 iterations to reach a conclusion. These metrics tell you whether your nervous system is healthy, whether agents are behaving as expected, and where bottlenecks are forming. Building this observability stack takes effort, but it is non-negotiable for production agent orchestration. Because when an autonomous agent makes a decision that affects a customer, an employee, or a financial transaction, you must be able to explain exactly what happened, why it happened, and what the agent did next. Anti-patterns, what not to do. I have spent most of this video describing what to build. Let me spend a few minutes on what to avoid, because the anti-patterns are just as important, and they are alarmingly common. Anti-pattern 1 is the God agent. This is a single copilot or bot that has been given direct access to every system in the organization. It can read email, update databases, provision users, and send payments. It is convenient because there is only one agent to maintain. It is also catastrophic because a single prompt injection or misclassification can cause damage across every system simultaneously. The nervous system architecture prevents this by constraining agents to high-level orchestrator calls rather than direct system access. Anti-pattern 2 is the secret graveyard. This is what happens when every bot has its own connection string, API key, or client secret stored in a different location. Some are in environment variables, some are in key vaults that nobody monitors, some are hard-coded in prompts or tool definitions. When a secret expires or is compromised, you have no central inventory of what breaks. The fix is managed identities and federation. There should be exactly 0 client secrets in your agent orchestration layer. Anti-pattern 3 is the stateless long runner. This is the workflow that was designed as stateless because someone read a benchmark showing that stateless is faster, but the process actually needs to wait for approvals, handle callbacks, and survive restarts. So the developer adds hacky workarounds. External databases store the state. Cron jobs poll for completion. And the resulting system is slower, more expensive, and less reliable than a native stateful workflow would have been. If your process lasts longer than 5 minutes or needs to survive interruptions, use stateful. The benchmark numbers do not matter if the architecture is wrong. Anti-pattern 4 is the human-in-the-loop everything approach. Some organizations are so afraid of autonomous agents that they require human approval for every single action. The result is a system that is technically automated but practically manual. Agents spend most of their time waiting for humans to click approve buttons, and the humans, overwhelmed by approval volume, start clicking approve without reading the context. This is neither efficient nor secure. The correct approach is to define risk-based guardrails, automate the low-risk actions, and reserve human review for the genuinely high-stakes decisions. Anti-pattern 5 is the skip standard movement. This happens when a team wants to save money or avoid Azure complexity, so they build their orchestration in consumption logic apps or Power Automate cloud flows. These platforms are excellent for their intended use cases. They are not excellent for enterprise-scale agent orchestration that requires custom connectors, virtual network integration, agent loop actions, and deep DevOps control. Skipping standard, because it seems harder, is a decision that creates technical debt from day one. The deployment roadmap from zero to nervous system. So the architecture works, the security works, the governance works, the observability works. The next question is how you actually start and how you avoid the common trap of trying to orchestrate everything on day one and failing. Here is a practical 7-phase roadmap. Phase 1 is inventory. You map every agent, bot, flow, and custom integration that currently exists in your environment. You document what systems each one touches, what credentials it uses, and what business processes it claims to support. This is not glamorous work, it is audit work, and it is essential because you cannot orchestrate what you cannot see. Phase 2 is selection. You identify one end-to-end process that crosses multiple systems and hurts when it breaks. Employee onboarding is a common choice because it touches HR systems, identity platforms, email provisioning, and security approvals. Partner order processing is another good candidate because it crosses organizational boundaries. Pick a process that is painful, visible, and has executive sponsorship. Do not pick the most complex process in the organization. You are building confidence, not proving a point. Phase 3 is design. You build the first orchestrator logic app for the selected process using Logic App Standard. You define the workflow triggers, the branching logic, the connector calls, and the error handling paths. You use stateful workflows because the process will involve waits and approvals. You use managed identities for every connection that stays inside your primary tenant. And you document the design so the security team can review it. Phase 4 is identity. You migrate every credential in the orchestrator to managed identities. For connections that need to reach other tenants, you configure workload identity federation with explicit trust relationships. You remove every client secret, every connection string, and every hard-coded token. You test every federated connection end-to-end. And you document the trust relationships in your identity governance catalog. Phase 5 is connectorization. You identify the proprietary business logic that your agents need to access. You wrap that logic in internal APIs with open API specifications. You publish those APIs as custom connectors in Logic Apps. You test the connectors, you version them, and you add them to your connector catalog so other teams can discover and reuse them. Phase 6 is agent integration. You introduce the first autonomous agent that calls the orchestrator instead of calling APIs directly. This might be a Copilot Studio agent, a Teams bot, or a custom Azure OpenAI agent. You configure it with a small set of high-level tools that map to Logic App endpoints. You test the full flow from user request through agent reasoning through orchestrator execution. You verify that the agent cannot bypass the orchestrator and access systems directly. And you measure the end-to-end latency and reliability. Phase 7 is expansion. You add more processes to the orchestration layer one at a time. You reuse existing connectors wherever possible. You share workflow patterns across teams. And you build the monitoring and alerting stacks so your operations team can see the health of the entire nervous system as it grows. This roadmap takes months, not weeks. But it works because it builds confidence incrementally. Each phase delivers a concrete, verifiable improvement. And by the time you reach phase 7, your organization has already seen the value of orchestration in production. The future of agent orchestration. But this is not just about fixing today's mess, it is about building for what is coming. And what is coming will make today's agent landscape look primitive. By late 2026 and into 2027, the capabilities of large language models will continue to accelerate. Agents will reason over longer contexts, plan more complex multi-step actions, and interact with richer multimodal inputs. New models will be released on schedules that make the current pace feel slow, and every agent you have built will need to upgrade its reasoning engine without breaking its execution layer. This is why the nervous system architecture is future-proof. When a new model becomes available, you update the agent loop action configuration to point to the new deployment. The orchestrator logic does not change. The business rules do not change. The cross-tenant connections do not change. Only the reasoning engine upgrades. And because the orchestrator constrains what the agent can do through typed custom connectors and governed workflow definitions, a more powerful model does not create new security risks. It simply makes better decisions within the same guardrails. Microsoft is also expanding Entra Agent ID with deeper governance features. Blueprint-based permission management will allow you to define entire classes of agents with standardized identity models, scoped permissions, and behavioral policies. You will be able to deploy a new agent that inherits the governance profile of its blueprint automatically, rather than configuring each agent's identity and permissions manually. Logic Apps Standard will continue to evolve with deeper AI integration, more connector coverage, and improved performance for stateful workflows. The gap between stateful and stateless throughput is already narrowing as the runtime optimizes storage patterns, and the integration with Azure Service Bus, Event Grid, and Kubernetes will make the orchestration layer even more capable for event-driven and containerized workloads. The shift from reactive triggers to proactive, event-driven agentic workflows is already underway. Instead of waiting for a user to ask a question, agents will monitor event streams, detect patterns, and initiate orchestrated processes before the user even knows they need something. A supply chain agent might notice an inventory anomaly, trigger a logic app that checks supplier availability across 3 tenants, and present the purchasing manager with a pre-validated order recommendation before the stockout occurs. This is the direction of travel. Agents will become more autonomous, processes will become more proactive, and the orchestration layer that governs them will become the most critical infrastructure in your cloud environment. The organizations that invest in this architecture now will not just survive the transition, they will define it. The Copilot Studio to Logic Apps Bridge. I have talked about the architecture in abstract terms. Let me get specific about how Copilot Studio and Logic Apps actually connect, because this is the bridge that most Microsoft-focused organizations need to build first. Copilot Studio excels at reasoning, natural language understanding, and conversational interaction. You define an agent with a description, knowledge sources, tools, and triggers. You enable generative orchestration so the agent can dynamically decide which tools to call based on the user's intent. And you publish the agent to channels like Teams, web chat, or email. The tool layer is where the integration happens. In Copilot Studio, a tool is an action that the agent can invoke to accomplish a task. By default, these tools are Power Platform connectors or AI prompts, but you can also call a Power Automate Cloudflow or an external HTTP endpoint. And that HTTP endpoint is your doorway into Logic Apps. Here's the practical pattern. You create a Logic app with an HTTP trigger that defines a specific business capability. The trigger schema specifies exactly what inputs the orchestrator expects. For example, an onboarding initiation trigger might expect employee name, start date, department, and security clearance level. The schema is typed and validated. There is no ambiguity about what the agent should provide. In Copilot Studio, you add a tool that calls this HTTP endpoint. You describe the tool in natural language so the generative orchestration engine knows when to use it. The description might say initiate cross-tenant employee onboarding when the user provides employee details and a start date. You configure authentication so the HTTP call uses the agent's credentials or a service principal that both systems trust. When a user asks the agent to onboard a new employee, the agent's reasoning loop analyzes the request. It determines that onboarding initiation is the right tool. It extracts the employee details from the conversation. It constructs the HTTP request with the required parameters, and it sends the request to the Logic App trigger. The Logic App receives the request, validates the schema, and starts the orchestration. It might branch immediately to handle different employee types. It might pause for approvals. It might call other Logic apps in different tenants. And when the process reaches a milestone or completion, it returns a structured response to the agent. The agent receives the response and incorporates it into its reasoning. It might tell the user that the onboarding process has started, that 3 approvals are pending, and that the new employee will receive a welcome email once the security review is complete. If the user asks follow-up questions, the agent can make additional orchestrator calls to check status, modify details, or escalate issues. This bridge is powerful because it preserves what Copilot Studio does well while delegating what it does poorly. The agent handles the conversation. The orchestrator handles the execution. The agent never touches a database directly. The orchestrator never tries to interpret natural language. Each system operates at the layer where it is strongest, and they communicate through well-defined HTTP contracts that both teams can understand, version, and test. Migrating from siloed bots, a real example. Let me walk through a migration scenario so you can see how this transition actually happens in practice. Imagine a manufacturing company that has grown through acquisition. They have 4 separate Microsoft 365 tenants from 3 prior companies, plus the original parent organization. Each tenant has its own copilot or bot for some local function. Tenant 1 has a Teams bot that handles IT support tickets. It connects directly to ServiceNow, reads knowledge bases from SharePoint, and sends notification emails through Exchange Online. Tenant 2 has a Copilot Studio agent that answers HR questions and can submit time-off requests to a legacy SAP system through a custom API. Tenant 3 has a Power Automate flow that monitors a shared mailbox for customer complaints and routes them to the appropriate regional team. Tenant 4 has a custom Azure OpenAI agent that summarizes production reports and emails them to managers. None of these agents know about each other, none share state. Each has its own credentials, its own error handling, and its own understanding of business rules. When the company decides to standardize employee onboarding across all 4 entities, the IT team realizes that no single bot can handle the end-to-end process because the process crosses every tenant boundary and touches every system. The migration starts with an inventory. The team documents every agent, every connection, every credential, and every business rule that each agent claims to implement. They discover that 3 different agents have their own logic for provisioning email accounts, each implemented slightly differently. 2 agents use the same ServiceNow connection, but with different user accounts. And 1 agent has a client secret that expired 6 months ago and was never renewed, meaning it has been failing silently on a subset of its tasks. Phase 2 is process selection. The team chooses contractor onboarding as the first orchestrated process because it is painful, visible, and cross-tenant by definition. They design a single Logic app in standard plan that lives in the primary tenant. The Logic app exposes an HTTP trigger for initiate contractor onboarding. It uses stateful workflows because the process involves approvals that can take several days. It uses managed identities for connections inside the primary tenant, and it configures workload identity federation for connections to the 3 subsidiary tenants. Phase 3 is connector creation. The team wraps the common capabilities into custom connectors. A provisioning connector handles mailbox and group assignments. A ServiceNow connector handles ticket creation and status checks. An HR system connector handles time-off requests and contractor status updates. Each connector is documented, versioned, and published to the organization's connector catalog. Phase 4 is agent integration. The IT support bot in Tenant 1 is updated so that instead of creating tickets directly in ServiceNow, it calls the orchestrator with a request to initiate onboarding. The HR agent in Tenant 2 is updated so that instead of calling the legacy SAP API directly, it calls the orchestrator with employee details. The complaint flow in Tenant 3 is updated so that high-priority complaints that require cross-tenant coordination are routed to the orchestrator instead of being handled locally. Phase 5 is decommissioning. As the orchestrator proves itself, the team gradually retires the direct connections that the individual bots were using. The duplicated provisioning logic is removed from the bots, the expired client secrets are revoked, and the direct SAP API access that the HR bot had is restricted so that only the orchestrator's managed identity can reach it. 6 months after starting the migration, the company has a single orchestration layer that handles contractor onboarding across all 4 tenants. The process is audited, compliant, and resilient to failures. The individual agents still exist, but they are thinner. They reason, they converse, they call the orchestrator, and the orchestrator remembers, coordinates, and executes. This is what migration looks like. It is not a big bang. It is incremental, it is architectural, and it works because each phase delivers a concrete, visible improvement that builds confidence for the next phase. Common objections answered. Whenever I present this architecture to leadership teams, I hear the same objections. Let me address them directly, because if you are going to sell this inside your organization, you need answers that are grounded in reality rather than enthusiasm. Objection 1 is that this is too complex. We already have bots that work. The question is why we would add another layer. The answer is that your bots work in isolation. They do not work in coordination. And the complexity of adding an orchestration layer is significantly less than the complexity of maintaining 15 point-to-point integrations that each have their own credentials, error handling, and business logic. The orchestrator is complex once, the point-to-point model is complex forever, and it multiplies with every new bot. Objection 2 is that Copilot Studio and Power Automate are good enough. We do not need Azure. The answer is that Copilot Studio handles reasoning brilliantly. Power Automate handles departmental automation well. Neither was designed for enterprise-grade cross-tenant orchestration with custom connectors, stateful long-running processes, and deep DevOps integration. Logic Apps Standard is the professional integration surface for exactly these scenarios. It is not a replacement for Copilot Studio or Power Automate. It is the layer beneath them that makes them enterprise-ready. Objection 3 is that our developers do not know Logic Apps. The answer is that Logic Apps Standard uses a designer experience that is familiar to anyone who has built Power Automate flows. The JSON workflow definitions are readable and version controllable. And the transition from citizen developer to integration professional is smoother than the transition from low-code to custom code in Azure Functions or Kubernetes. If your team can build a Power Automate flow, they can build a Logic app. The gap is smaller than most people assume. Objection 4 is that managed identities and federation are too hard to configure. The answer is that they are harder than copying a client secret, and they should be. The extra configuration is the security. Every federated trust relationship you create is explicit, documented, and auditable. Every managed identity you assign is automatically rotated by the platform, and every secret you avoid is one less credential that your security team has to track, rotate, and worry about being stolen. The difficulty is the feature. Objection 5 is that stateful workflows are too slow. The answer is that stateful workflows add input-output overhead, and that does increase latency per action. But for the processes that matter most to autonomous agents, the durability and observability are worth the speed trade-off. You use stateless workflows for the fast synchronous paths. You use stateful workflows for the long-running processes that need to survive restarts and waits. The correct architecture uses both, and the benchmark numbers only matter when you choose the wrong type for the wrong job. Objection 6 is that this is overkill for our current scale. The answer is that architecture decisions are not about today's scale. They are about tomorrow's scale. If you build point-to-point integrations today, you are building the exact technical debt that will prevent you from adding the next agent, the next tenant, or the next business process. An orchestration layer is not overkill. It is insurance against the future complexity that every growing organization eventually faces. The 30-day pilot plan. If you are convinced and you want to start, here is a concrete 30-day pilot plan that delivers a working orchestrator without boiling the ocean. Week 1 is discovery. Spend 5 days mapping one specific process that hurts. Document every system it touches, every team involved, and every failure mode that currently wastes time. Do not try to map your entire agent estate. Pick one process. If you cannot identify a single process that crosses 2 or more systems and fails at least once a month, then your organization is not ready for orchestration. Solve that first. Week 2 is design. Spend 3 days designing the orchestrator logic app for your chosen process. Define the trigger schema. Map the workflow branches. Identify which connections can use managed identities and which will need federation. Sketch the error handling paths. And create a simple custom connector if your process touches an internal API. Do not build everything. Build enough to prove the pattern. Spend 2 days on identity configuration. Set up the managed identity for your logic app. Configure the federated trust for any cross-tenant connections. Test each trust end-to-end with a simple HTTP request. Document the configuration so your security team can review it. And do not proceed to week 3 until every identity connection works in isolation. Week 3 is build and test. Build the workflow in Logic Apps Standard. Use the designer for the main structure and switch to code view for fine-tuning. Test each branch independently. Simulate failures by temporarily breaking connections. Verify that your error handling paths fire correctly, and test the full end-to-end flow at least 3 times with different input scenarios. Week 4 is integration and demo. Connect your existing agent to the orchestrator trigger. This might be a Copilot Studio tool, a Power Automate flow that calls an HTTP endpoint, or a simple test script. Run the full flow from agent request through orchestrator execution. Capture the run history, show the logs to your security team, and present the results to stakeholders with concrete metrics. Time saved, errors caught, manual handoffs eliminated. At the end of 30 days, you will not have a full nervous system, but you will have proof. You will have a working orchestrator that handles one real process with real credentials, real error handling, and real cross-system coordination. And that proof is what you need to justify the next phase of investment. If the pilot works, you scale. If it does not work, you learned what broke before you committed to a full migration. Either outcome is valuable. The only losing move is to keep building siloed agents and hope the problem solves itself. It will not. It will get worse. Power Automate versus Logic Apps, where each belongs. I want to be clear about the relationship between Power Automate and Logic Apps because this confuses a lot of teams, and confusion here leads to bad architecture decisions. Power Automate is designed for citizen developers and business users. It is tightly integrated into Microsoft 365. It has a friendly low-code interface. It handles departmental automation, personal productivity workflows, and simple approvals with grace. If a business analyst needs to send a notification when a SharePoint list item changes, Power Automate is the right tool. It takes 10 minutes to build, it lives inside the business user's world, and it does not require Azure expertise. Logic Apps is designed for integration professionals and developers. It lives in Azure. It supports advanced networking, custom connectors, code-first workflow definitions, and deep DevOps integration. It is the professional surface for building integration backbones, stateful orchestrations, and cross-tenant coordination. If an architect needs to build a nervous system that governs agent behavior across business units and multiple Entra directories, Logic Apps is the right tool. The two platforms share the same underlying workflow engine, they share many connectors, and they can call each other. A Power Automate flow can trigger a Logic app. A Logic app can call a Power Automate flow. This is not an either-or choice. It is a both-and choice, with each platform handling the layer where it is strongest. The mistake is to try to make Power Automate do everything. When a business user builds a flow that grows to touch 5 systems, handle error routing, and coordinate across tenants, that flow has outgrown Power Automate. It has become an integration workload that needs the governance, observability, and lifecycle management that Logic Apps provides. The correct response is not to restrict the business user's creativity. It is to migrate that flow into Logic Apps Standard and expose it back to the business user through a well-defined connector or HTTP endpoint. The nervous system architecture does not replace Power Power Automate, it elevates it. Business users continue to build flows for local automation. But when those flows need to participate in enterprise-wide processes, they call the orchestrator. The orchestrator handles the complexity. The business user keeps the simplicity, and the architecture scales without creating sprawl. The economics of orchestration. Before I close, let me address the question that every CFO and every IT budget owner will ask. They want to know what this costs and what it saves. The cost side is straightforward. Compute for Logic Apps standard sits on either an app service plan or a functions premium plan. For a moderate enterprise workload, you are looking at a few $100 to a few $1,000 per month in compute, depending on the number of instances, the geographic distribution, and the storage requirements for stateful workflows. This is predictable infrastructure cost, not per action billing that surprises you at the end of the month. Custom connectors add a small amount of development overhead. You need someone who can write or maintain open API specifications. You need a CI/CD pipeline that can deploy connector updates. And you need governance review for each new connector operation. This is not free, but it is significantly cheaper than maintaining duplicate integration logic inside a dozen different bots. Workload identity federation requires Entra configuration work. Setting up federated credentials, cross-tenant trust relationships, and conditional access policies takes time from your identity team. This is front-loaded effort. Once the trusts are configured, they run automatically. And the ongoing operational cost is lower than the manual secret rotation and incident response that client secrets demand. The savings side is where the business case becomes compelling. Every point-to-point integration that you replace with a connector-based orchestration eliminates duplicate logic. When a business rule changes, you update the orchestrator once instead of updating 6 bots. When an API changes, you update the custom connector once instead of fixing raw HTTP calls scattered across multiple agents. And when a credential needs rotation, you update the managed identity trust once instead of scrambling to find every place a secret was embedded. The bigger savings are in risk reduction. A compliance audit that finds scattered credentials, undocumented API access, and inconsistent business logic is expensive. It triggers remediation projects, security reviews, and sometimes regulatory findings. An orchestration architecture with centralized logging, managed identities, and governed connectors is auditable by design. The security team can answer questions about who can access what, when they accessed it, and what they did. This is not a soft benefit. It is a hard cost avoidance that most organizations only appreciate after they have suffered through a bad audit. The team structure question is equally important. You do not need a new army of Azure developers. You need a small integration team, perhaps 2 or 3 people, who understand Logic App Standard, Entra Identity, and Open API. They build the orchestrator, maintain the connectors, and manage the cross-tenant trusts. Business users and citizen developers continue to build agents in Copilot Studio and flows in Power Automate, but they call the orchestrator instead of wiring direct connections. The division of labor is clean, the skill requirements are reasonable, and the organizational change is smaller than most people fear. The return on investment for this architecture is not immediate. It compounds. Month 1 delivers a working pilot. Month 6 delivers the first migrated process with measurable time savings. Month 12 delivers audit-ready governance and the ability to add new agents without adding new integration debt. And month 18 delivers the strategic flexibility to adopt new AI models, new tenants, and new business partnerships without rebuilding your integration layer from scratch. That is the economics. Upfront investment in architecture, ongoing savings in maintenance, and compounding returns in speed, security, and scale. The one question before your next agent project. Before you greenlight your next copilot, your next bot, or your next automation project, ask one question. Consider whether this agent needs to coordinate with other agents, systems, or tenants to complete a real business process. If the answer is no, build it in isolation. Use Copilot Studio, use Power Automate, solve the local problem, and move on. But if the answer is yes, do not build another silo. Do not wire another point-to-point connection that your future self will curse in 12 months. Do not pretend that a chatbot with direct API access is an enterprise architecture. It is not. It is a demo that escaped into production. Instead, build the nervous system first. Design the orchestrator, define the connectors, configure the identities, and then let your agents plug into something that can remember, coordinate, and recover. The agents will be thinner, they will be cheaper to maintain, and they will be capable of things that isolated bots can never achieve. This is the shift from building intelligent tools to building intelligent systems. Tools impress in demos, systems deliver in production, and the gap between the two is where most agent investments go to die. Agents do not fail because of bad AI, they fail because of missing orchestration. Every impressive demo becomes a liability when it is wired directly to a dozen APIs with no central state, no cross-tenant governance, and no recovery plan. Azure Logic Apps Standard, stateful workflows, managed identities, custom connectors, and workload identity federation form the nervous system that makes autonomous agents enterprise-ready. Agents reason, orchestrators execute. That is the architecture that scales across tenants, survives failures, and proves compliance to auditors. If this changed how you think about agent architecture, follow me on LinkedIn. And if you want the next deep dive on deploying your first orchestrator in production, the next video in this series is already in production.